A point of infinite density hides within our universe, warping the fabric of reality itself. Black holes are no longer just theory. They are cosmic laboratories forcing us to rewrite the rules of physics. By the end of this journey, you will understand 25 discoveries that are fundamentally changing our conception of space, time, and existence. We will uncover why a black hole is not truly black and how its death might hold the key to the universe's deepest secrets. How does it feel to know our most basic laws of physics are being challenged by the darkness? The silence of the cosmos was broken by a whisper in 2015. For the first time, humanity felt the fabric of spacetime itself ripple. This was the direct detection of gravitational waves, a century-old prediction from Einstein finally confirmed. The source was a violent dance a billion light-years away, where two black holes, one 29 times and the other 36 times the mass of our Sun, spiraled into each other. Their cataclysmic merger sent a tremor through the universe, a vibration so subtle it took one of the most sensitive instruments ever built to sense it. That instrument is LIGO, the Laser Interferometer Gravitational Wave Observatory. It works by splitting a laser beam down two long, perpendicular arms, each 4 kilometers long. A passing gravitational wave minutely stretches one arm while squeezing the other, creating a tiny shift in the laser light that reveals the cosmic disturbance. This was not just a confirmation of a theory, it was the opening of a new sense. As physicist Kip Thorne and others have stressed, we are no longer just looking at the universe, we are now listening to it. We can hear the invisible, the dark collisions of black holes that emit no light. Each chirp and rumble we capture tells a story of immense masses, frantic spins, and the pure geometry of warped space. How might this change our entire approach to astronomy? It transforms our understanding from a silent movie to a rich symphony, where every crash and merger writes a new chapter in the life of the cosmos. This new sense reveals a universe far more dynamic and violent than we ever knew, built not on stillness but on constant, rhythmic collision. But what if the black hole itself could glow? This is the startling prediction that came from Stephen Hawking, a revelation so profound it redefined the very nature of these cosmic traps. Hawking proposed that black holes are not truly black at all. They possess a faint, theoretical glow, a whisper of radiation now known as Hawking radiation. This is not light escaping from within the event horizon. Nothing can do that. Instead, it is a ghostly theft of energy from the black hole's own gravitational grip, a process born from the chaotic quantum foam that permeates all of space. To understand this, picture the empty vacuum of space. It is not truly empty, but a seething sea of virtual particles, pairs of matter and antimatter that constantly flicker in and out of existence, borrowing energy from the universe for the briefest instant before annihilating each other and repaying the debt. Now imagine this happening right at the precipice of a black hole, at the very edge of its event horizon. In this extreme environment, one of these virtual particles might fall inward, while its partner escapes into the wider universe. The escaped particle becomes real, stealing a tiny amount of energy from the black hole's gravitational field to pay its debt to reality. This stolen energy is Hawking radiation. From our perspective, the black hole has just emitted a particle, and in doing so, it has lost a minuscule amount of mass. This process is incredibly slow for a typical black hole. A black hole with the mass of our Sun would take far, far longer than the current age of the universe to evaporate in this way. Yet, for smaller, theoretical black holes, this evaporation could be rapid and dramatic, ending in a final, theoretical burst of energy. Hawking's brilliant insight gave black holes a temperature connecting the world of the immensely large, governed by gravity, with the world of the incredibly small, ruled by quantum mechanics. It challenges the idea of a permanent black hole, suggesting that even these cosmic titans have a lifespan, a potential end state governed by the laws of physics. This evaporation raises a deep and troubling question for physicists. What happens to all the information about the material that fell into the black hole? According to quantum mechanics, information cannot be destroyed, but if a black hole evaporates completely, leaving behind only a featureless burst of radiation, where did that information go? This black hole information paradox is one of the greatest unsolved problems in theoretical physics, a direct conflict between general relativity and quantum mechanics. The slow, steady whisper of Hawking radiation forces us to ask, what is the ultimate fate of a black hole, and what secrets does its death reveal about the fundamental rules of our universe? For decades, that faint theoretical glow was our only hint, but then we saw it. In April 2019, the world witnessed a scientific miracle, the first direct image of a black hole. The Event Horizon Telescope collaboration unveiled a fiery ring of orange and yellow, a cosmic donut of light swirling around the profound darkness of the supermassive black hole at the heart of galaxy M87. This was not an artist's impression, it was a photograph of shadow and light, 6.5 billion times more massive than our own sun. To capture an object so distant required an instrument the size of the entire Earth. The team synchronized a global network of radio telescopes, from the high deserts of Chile to the peaks of Hawaii and even the South Pole. By combining their signals, they created a virtual dish as wide as our planet, a telescope with a resolution sharp enough to read a newspaper in New York from a sidewalk cafe in Paris. The central shadow you see is the black hole's event horizon silhouetted against the hot, glowing material of its accretion disk. The intense gravity bends the light from this disk, wrapping it around the void in a perfect circle of fire. This bright ring is made of photons that are not escaping from the black hole, but are actually orbiting it, trapped in circular paths before some finally break free and travel across the universe to our telescopes. Scientists like Shepard Doleman, the project's founding director, emphasized that this image does more than just confirm these objects exist. It provides a direct test of Einstein's general relativity in the most extreme gravitational environment imaginable. The size and shape of that shadow matched the predictions of his theory with stunning accuracy. Processing the data was a Herculean task. The telescopes collected so much information it could not be sent over the internet. It had to be physically flown on half a ton of hard drives to central processing centers. Teams then spent years using sophisticated algorithms to piece together the fragments into a coherent picture, comparing the results against millions of simulations to ensure what they were seeing was real. This single image opens a new era of visual astronomy for black holes. Future observations will capture movies showing how the fiery ring changes over time. This will allow scientists to measure the black hole's spin, understand how it launches powerful jets of particles thousands of light years into space, and ultimately learn how these cosmic engines shape the galaxies they call home. We have moved from hearing their collisions to staring directly into their abyss. What new truths will we find written in that circle of light? That fiery ring in a distant galaxy was just the beginning, for a far closer giant has now had its portrait taken. At the very heart of our own Milky Way, a silent titan reigns. This is Sagittarius, a star, a supermassive black hole with a mass of over 4 million suns. Its existence was not proven by a single image, but by watching the frantic orbits of stars around an invisible point of immense gravity. For decades, astronomers like Andrea Ghez and her team tracked these stellar dancers, charting their paths as they whipped around the galactic center at breathtaking speeds. One star, known as S2, completes its elliptical orbit in just 16 years, traveling at over 15 million miles per hour at its closest approach. By meticulously mapping these stellar trajectories, scientists could weigh the invisible anchor at the center, confirming with exquisite precision the presence and mass of Sagittarius, a star. This is not a unique phenomenon. We now believe that nearly every large galaxy, including our nearest major neighbor, Andromeda, hosts a supermassive black hole at its core. These are not mere residents, they are the fundamental architects of their cosmic homes. An extraordinary correlation exists, a cosmic handshake between the black hole and its galaxy. The mass of the central black hole is directly proportional to the mass of the galaxy's central bulge of stars. This tight relationship suggests they did not just grow independently, they grew up together in a process of co-evolution spanning billions of years. But how did these giants form so quickly in the early universe? One leading theory points to direct collapse. In the dense, pristine gas of the infant cosmos, vast clouds could have collapsed under their own gravity, bypassing the star formation stage entirely and directly birthing a massive seed black hole, tens of thousands of times the mass of our Sun. These seeds would then feast on the surrounding gas, growing rapidly into the supermassive behemoths we see today. Their growth is not a quiet process. When a supermassive black hole actively feeds, it can become a quasar, an engine of light so powerful it can outshine its entire host galaxy. The energy released from the infalling material is staggering, and this energy does not just vanish. It is poured back into the galaxy, heating up surrounding gas and driving powerful winds. This phenomenal output acts as a cosmic regulator. By heating the raw material for new stars, the black hole can effectively put the brakes on star formation, preventing the galaxy from growing too large too fast. It is a delicate feedback loop, a gravitational conversation between the monster at the center and the galaxy it both builds and controls. The existence of these central giants forces us to see the cosmos as a deeply interconnected web, where the smallest point of infinite density can dictate the fate of hundreds of billions of stars. The stellar corpses and galactic giants are not the whole story, for a hidden population of middleweight black holes may hold the key to our cosmic history. These are the intermediate mass black holes, with masses ranging from hundreds to hundreds of thousands of times that of our Sun. They represent a crucial missing link, the potential stepping stones between the black holes formed from dying stars and the supermassive titans that rule galactic centers. For years, their existence was largely theoretical, but then the cosmos sent us a signal. In May of 2019, the LIGO and Virgo observatories detected a gravitational wave event known as GW190521. The ripple told a story of a collision between two unexpected objects, black holes of about 66 and 85 solar masses. Their merger created a final black hole of 142 solar masses, placing it squarely in the intermediate mass range for the very first time. This was not just a detection, it was a revelation. The parent black holes themselves were puzzling, as they existed in a mass range thought to be forbidden by standard stellar evolution. Their very existence points to more complex origins. Perhaps they were themselves the products of earlier mergers in a dense cosmic environment. Where do such events occur? Dense stellar nurseries known as globular clusters are prime candidates. Imagine a sphere packed with millions of stars, all gravitationally bound in a tight cosmic dance. In such a crowded neighborhood, stellar collisions and mergers are far more likely. A black hole could form there and then steadily grow by consuming other stars or merging with other black holes, slowly building its mass over billions of years. This process provides a plausible pathway for creating the seeds that would later evolve into supermassive black holes. The hunt for these elusive objects continues through other methods as well. Astronomers scrutinize the motions of stars within globular clusters, looking for the telltale gravitational tug of an unseen, massive object. They also search for the faint X-ray glow of gas being heated as it spirals into one of these middleweight black holes. Each candidate discovery adds another piece to the puzzle. How common are these intermediate black holes, and do they ultimately settle in the hearts of galaxies, becoming the supermassive engines we see today? Their discovery forces us to rewrite the story of black hole growth, suggesting a universe where these dark objects can build themselves up through a series of violent mergers, a hierarchical climb from stellar corpse to galactic master. This missing link completes a picture of black holes existing across all scales, from the small to the unimaginably large, all playing their part in the evolution of the cosmos. But a black hole is not a static pit, it is a cosmic whirlpool. Its rotation twists the very fabric of the universe around it, an effect predicted by Einstein known as frame dragging. Imagine dipping a spinning sphere into a thick fluid. The liquid around it would be pulled into a whirl. A rotating black hole does this to spacetime itself, dragging the empty void along with it as it turns. This spin is not a trivial detail. It is a fundamental property that dictates how a black hole interacts with the cosmos. Scientists measure this rotation by studying the X-ray light from the superheated gas of the accretion disk. As material spirals inward, the intense gravity and magnetic fields heat it to millions of degrees, causing it to glow in high-energy X-rays. The precise properties of this light, analyzed by researchers like Ramesh Narayan, reveal how fast the black hole is spinning. Some have been clocked rotating at nearly the maximum speed allowed by physics, a significant fraction of the speed of light. This frantic rotation carves out a bizarre region of space just outside the event horizon called the ergosphere. Here, the frame dragging is so powerful that nothing can stand still, not even space itself. Every object is forced to move in the direction of the black hole's spin. This strange property opens the door to one of the most fantastical ideas in theoretical physics, the Penrose process. In theory, an object could fly into the ergosphere and split in two. One part falls into the black hole, while the other escapes with more energy than the original object entered with. The black hole itself has effectively lost a tiny amount of rotational energy, which is now powering the escaped fragment. While this is a theoretical idea for spacecraft, nature performs its own version on a colossal scale. The spin of a supermassive black hole is likely the engine that powers the immense relativistic jets seen erupting from active galaxies. These are beams of matter and energy shot out from the poles at nearly the speed of light, stretching for thousands of light years. The rotational energy of the black hole, channeled by powerful magnetic fields, is what can launch these spectacular cosmic geysers. This spin also leaves its signature in the final moments of a black hole merger. When two spinning black holes spiral together, their individual rotations affect the complex dance, imprinting a specific pattern on the resulting gravitational waves. By reading these subtle wobbles and chirps, scientists can decipher the spin of the original black holes, learning about their history and formation. The simple act of rotation transforms a black hole from a passive trap into a dynamic, energy-producing engine. It connects the quiet spin of a stellar corpse to the galaxy-shaping power of a central supermassive giant. What other cosmic secrets are encoded in the silent, relentless turning of these dark spheres? Yet the slow evaporation Hawking predicted creates a profound dilemma. What happens to all the information about the things that fell in? Every star, every planet, every atom carries a specific identity, a unique story encoded in its quantum properties. According to the bedrock laws of quantum mechanics, this information can never be truly destroyed. It can be scrambled but never erased from the universe. If a black hole evaporates completely, leaving behind only a featureless puff of heat, then all that intricate information has seemingly vanished into nothingness. This is the black hole information paradox, a direct conflict between the smooth spacetime of general relativity and the strict information preservation of quantum mechanics. It suggests our fundamental understanding of physics is deeply incomplete. This paradox is the forcing function driving physicists toward a theory of everything, a framework known as quantum gravity that seeks to merge the large and the small. Competing ideas like string theory, which proposes that fundamental entities are tiny vibrating strings, or loop quantum gravity, which suggests spacetime itself is woven from discrete loops, both attempt to resolve this tension. They try to answer where the information goes. One of the most mind-bending proposals is the holographic principle. It suggests that all the information about everything within a black hole's three-dimensional volume is not lost inside, but is instead perfectly encoded on its two-dimensional surface, the event horizon. Imagine the entirety of a three-dimensional movie being stored on a flat, two-dimensional DVD. The surface of the black hole would act like that cosmic DVD, with every bit of information about what fell in painted onto it in Planck-scale pixels. This leads to other radical ideas like the firewall hypothesis. If the information is stored on the horizon, does that mean an astronaut crossing it would not experience empty space, but would instead be instantly incinerated by a wall of energy, a paradox in its own right? The mathematics of entanglement entropy offers another clue. The particles of Hawking radiation emitted by the black hole may be quantum entangled with the information inside or with the horizon itself. Sophisticated calculations now suggest that as the black hole evaporates, this entanglement could transfer the information out, imprinted onto the radiation in an incredibly complex code. The black hole's final burst would not be random noise, but a release of all the scrambled data. Resolving this is not just an academic exercise. It forces us to ask what reality truly is at its most fundamental level. Is spacetime smooth and continuous, or is it pixelated? Do the laws of physics break down at a singularity, or are they simply being rewritten? The humble black hole, a seemingly simple object defined only by its mass, spin, and charge, may in fact be the most complex information processing system in the universe. Its silent evaporation could be the key that unlocks a unified theory of nature itself. The paradox of information is not the only mystery, for black holes may have been present from the very first moments of creation. These are primordial black holes, hypothetical objects born not from dying stars, but from the intense pressures of the infant universe. In the seething chaos that followed the Big Bang, tiny regions of space could have been squeezed to unimaginable density. A simple overdensity, a knot in the fabric of spacetime, might have collapsed directly into a black hole. The possible mass range for these ancient relics is staggering, from lighter than a paperclip to heavier than a large asteroid. This opens a radical possibility that a vast, unseen population of these primordial objects could be drifting through the cosmos right now, perhaps even passing through our solar system undetected. For decades, scientists like Bernard Carr have theorized that these primordial black holes could solve a major cosmic puzzle. They might be a significant component of the dark matter that binds galaxies together. While we cannot see dark matter, we feel its gravitational influence everywhere. If countless asteroid mass black holes were sprinkled throughout galactic halos, their collective gravity would perfectly explain the rotational speeds of galaxies without the need for exotic new particles. The challenge, of course, is finding them. Their small size and darkness make them nearly impossible to see directly, but we can look for their gravitational fingerprints. One method is gravitational microlensing. If a primordial black hole passes directly between us and a distant star, its gravity will act as a lens, bending the starlight and causing the star to temporarily brighten. Surveys scanning millions of stars have looked for these telltale flashes, placing limits on how many could exist. another signature comes from their theoretical demise. A very small primordial black hole, one with the mass of a mountain, would be evaporating now due to Hawking radiation. Its final moments would be a spectacular burst of high-energy gamma rays. Astronomers have searched for these specific signals in the sky, a potential flash marking the death of a universe-born relic. While no confirmed detection has been made, the search continues with more sensitive instruments. The formation of these objects is also deeply tied to the conditions of the early universe. They could have been forged in the violent transitions of cosmic inflation, or from the collisions of bizarre structures known as cosmic strings. If they were abundant enough, primordial black holes could have acted as seeds for the supermassive black holes we see in galactic centers today, providing a ready-made starting point for rapid growth. Their potential influence extends to the cosmic microwave background, the leftover heat from the Big Bang, as their evaporation could have subtly altered this ancient light. Future observatories like the Laser Interferometer Space Antenna, LISA, may be able to hear the gravitational wave hum from a vast population of these small black holes. The existence of primordial black holes would fundamentally expand the black hole family tree, revealing them as not just end-of-life phenomena, but as potential building blocks of the cosmos itself. What if the darkness we attribute to an unknown particle is actually made of countless ancient fragments of spacetime, a hidden population of cosmic fossils from the dawn of time? The profound connection between information and evaporation led to an even deeper truth, that black holes themselves possess a temperature and obey their own version of the laws of thermodynamics. This idea, pioneered by the young physicist Jacob Bekenstein and later refined by Stephen Hawking, completely reshaped our understanding of these cosmic objects. Bekenstein made the radical suggestion that a black hole must have entropy, a measure of disorder or hidden information. In everyday systems, entropy tends to increase, and Bekenstein proposed that when matter-carrying entropy falls into a black hole, the total entropy of the universe still goes up because the black hole's own entropy increases to compensate. Its entropy, he argued, is proportional to the area of its event horizon. This was a stunning revelation, for it linked the intangible concept of information directly to the physical geometry of spacetime. Hawking initially resisted this idea, as any object with entropy must also have a temperature, and a black hole with a temperature should glow, which seemed impossible. Yet his own subsequent work on Hawking radiation proved that they do indeed have a temperature, confirming Bekenstein's profound intuition. This established black hole thermodynamics, a set of laws perfectly analogous to the classical laws of thermodynamics. The first law connects energy conservation to the black hole's mass, spin, and charge. The second law, a cornerstone of this framework, states that the total area of all event horizons in the universe, which corresponds to the total entropy, can never decrease. When two black holes merge, the area of the new, larger event horizon is always greater than the sum of the areas of the original two. The universe's disorder has increased, mirroring the way entropy behaves in a closed box of gas. But what does it mean for a black hole to have entropy, and why is that number so astronomically large? For a black hole with the mass of our Sun, the entropy is a number with 78 digits. This is an unimaginable amount of hidden information, far exceeding the entropy of the star that collapsed to form it. This immense number hints at the microscopic structure of spacetime at the quantum level. According to this view, the event horizon is not a smooth, featureless surface. Instead, it may be tiled with incredibly tiny, discrete units of area, each one a fundamental pixel of spacetime capable of storing a single bit of information. Theories like string theory provide a way to count these quantum states. For certain types of black holes, string theory calculations can precisely account for the vast entropy by counting the different ways the strings that make up the black hole can vibrate and arrange themselves. The result matches the prediction from the event horizon's area with stunning accuracy. This is a powerful clue that we are on the right path toward a theory of quantum gravity. The thermodynamics of black holes is no mere analogy. It is a fundamental description of their nature. It tells us that a black hole is the most efficient information storage device in the universe, and its silent, dark surface is in fact a buzzing hive of quantum activity. What other secrets about the fabric of reality are written in the silent, orderly laws that these most disordered objects obey? The matter spiraling toward a black hole does not fall silently. It is caught in a furious cosmic whirlpool, an accretion disk of superheated gas and dust that glows with the intensity of 1 billion suns. This is the final, frantic dance before the void, a place where friction and immense gravitational forces heat material to millions of degrees, causing it to radiate across the entire electromagnetic spectrum. From radio waves to blistering gamma rays, this luminous disk is the primary beacon by which we study these dark objects. Yet, even more spectacular are the relativistic jets that erupt from the poles of many active black holes. These are narrow beams of charged particles, accelerated to over 99% of the speed of light and shot thousands of light years out into intergalactic space. The jet from the supermassive black hole in galaxy M87, which we have now imaged, stretches for at least 5,000 light-years from its core, a cosmic geyser of matter and energy. How can a black hole, an object known for its insatiable gravity, also be the most powerful engine for ejection in the universe? The answer lies in a delicate partnership between the black hole's spin and its magnetic fields. As the black hole rotates, it twists the magnetic fields embedded in its accretion disk, winding them into a powerful, coiled spring. Theorists like Roger Blandford have proposed a mechanism where this spinning magnetic field acts like a gigantic sling, tapping the rotational energy of the black hole itself to fling material outward along its poles. This process, a theoretical model involving the black hole's ergosphere, transforms the black hole from a passive trap into an active, universe-shaping force. The structure of the accretion disk itself dictates the nature of the show. In a standard thin disk, matter orbits in an orderly fashion, steadily spiraling inward and glowing brightly. But in systems where the accretion rate is lower, a different structure can form, an advection-dominated flow. Here, the gas is so hot and thin that it cannot radiate its energy away efficiently, so it carries most of its heat with it as it plunges inward, creating a fainter but hotter inflow. These different disk states produce different types of radiation, allowing astronomers to diagnose the feeding habits of the black hole from the X-rays and gamma rays it emits. This dynamic is not limited to galactic giants. Within our own Milky Way, stellar mass black holes in binary systems can become microquasars, miniature versions of their supermassive cousins, complete with their own brilliant accretion disks and powerful, albeit smaller, relativistic jets. The energy released from this accretion and jet formation does not simply vanish into the darkness. It pours back into the surrounding galaxy with tremendous force. These jets can blast through clouds of star-forming gas, heating it and pushing it away, effectively shutting down the birth of new stars. This is a profound form of feedback, a gravitational conversation where the black hole at the center regulates the growth of its entire galactic home. The brightest objects in the universe, quasars, are powered by this very process, where a supermassive black hole feasts on a vast reservoir of gas and announces its presence with a beacon of light that can outshine 1 trillion stars. This interplay reveals black holes as the ultimate cosmic regulators, their violent appetites and energetic outflows intimately woven into the life cycle of galaxies. The silent dance of two black holes ends in a cosmic shudder. These are black hole binaries, pairs of stellar corpses locked in a gravitational embrace, destined for a final, violent collision. The data from LIGO and Virgo reveals these events are not rare. the universe is filled with the quiet rhythm of these mergers. The rate at which they occur tells a profound story about the life and death of massive stars. Each detected event, like the historic GW150914, which witnessed the merger of two black holes roughly 30 times the mass of our Sun, challenges our old models of stellar evolution. We never knew such heavy black holes could be so common, forcing us to consider new pathways for their birth. How do these dark pairs even form? One path is the quiet evolution of a binary star system. Two massive stars are born together, they live their lives as companions, and eventually they both explode as supernova. If the conditions are just right, both leave behind black holes that remain gravitationally bound, their orbits slowly tightening over eons until they finally merge. The other path is far more chaotic, born in the dense stellar cities known as globular clusters. Here, in the crowded core, black holes can gravitationally find each other, forming pairs through dynamic interactions and exchanges. It is a cosmic dance where partners are swapped in a frantic gravitational ballroom. The masses and spins of the merging black holes are the final clues they leave behind. The prevalence of black holes in the 20 to 50 solar mass range, a so-called mass gap, suggests that some may be the products of previous mergers themselves, hierarchical builds in a dense environment. Their spin measurements are equally telling. A slow, aligned spin points to a calm, isolated binary evolution, while a random, tilted spin hints at a violent dynamical capture in a cluster. By compiling these statistics, scientists can begin to map the invisible population of black holes drifting through the darkness. This census extends across cosmic time. The merger rate was not constant. It likely peaked billions of years ago during a more crowded and vibrant epoch of star formation. By listening to the gravitational waves from different distances, which correspond to different look-back times, we can trace the history of stellar death and black hole creation throughout the universe's lifetime. Each chirp is a timestamp from a distant era. This relentless accumulation of data does more than just count collisions. It provides the most extreme tests of Einstein's general relativity, probing the theory in regimes of gravity and speed far beyond anything we can recreate. The universe is performing the experiments for us, and with every merger we record, we learn a little more about the hidden architecture of spacetime and the dark, orbiting pairs that shape it. Despite their terrifying complexity, a black hole is fundamentally simple. According to one of the most elegant ideas in physics, the No-Hair Theorem, a black hole can be completely described by just three numbers: its mass, its spin, and its electric charge. Every other detail, every shred of information about the stars, planets, or gas that fell in, is permanently lost behind the event horizon. A black hole has no hair, no unique features or distinguishing frizz. It is a perfectly smooth, bald sphere of pure gravity. This stunning simplicity emerges directly from the equations of general relativity, suggesting that once matter crosses the threshold, its identity is erased, leaving behind only these three cosmic fingerprints. This makes modeling their interactions beautifully straightforward. When two black holes spiral together, the gravitational waves they produce are a pure song of mass and spin, a waveform dictated almost entirely by these two parameters. The resulting black hole that forms from the merger will itself settle down into a new, simple state defined only by its new mass and new spin. It is as if the universe has a cosmic eraser, wiping the slate clean and leaving only the most essential gravitational signature. But what if this elegant picture is not the entire story? The unsettling whisper of quantum mechanics suggests there might be more to a black hole than just mass, spin, and charge. Theorists now explore the possibility of quantum hair, subtle deviations from perfect smoothness imprinted on the event horizon. These would not be physical hairs, but tiny quantum fields or structures that could encode information about what fell inside, a faint memory preserved on the surface. Detecting this quantum hair would require exquisitely precise measurements. Future gravitational wave observatories with far greater sensitivity might be able to listen for the faintest of echoes in the ring-down after a merger, a subtle wobble that betrays the presence of these quantum features. What would it mean if we found such a violation? It would be a direct signal that our understanding of gravity is incomplete, a crack in the perfect facade of general relativity through which the quantum world leaks out. It would force us to rewrite the No-Hair Theorem, trading its beautiful simplicity for a richer, more nuanced reality where black holes remember their past. This principle stands at a crossroads, representing both the breathtaking elegance of Einstein's theory and its ultimate limitation. The silent, dark spheres we study may be the simplest complex objects in the universe, their serene outward appearance hiding a storm of quantum possibility just beneath the surface. The elegant simplicity of the No-Hair Theorem gives way to a far more bizarre possibility, where the geometry of a spinning black hole twists reality into a knot. The Kerr metric, a solution to Einstein's equations for a rotating black hole, describes a spacetime so warped that it might permit pathways to other times and places. At the heart of this solution lies the theoretical potential for closed time-like curves, paths through spacetime that loop back on themselves. An astronaut traveling along such a curve could, in theory, journey into their own past. This is not magic, it is a direct, if profoundly strange, consequence of the equations that govern gravity. The intense frame dragging of a rapidly spinning Kerr black hole could twist the fabric of the universe into a tunnel, a wormhole. Picture a piece of paper folded so that two distant points touch. A wormhole would be a bridge connecting them, a cosmic shortcut. You could step into a portal near Earth and emerge instantly in a galaxy millions of light years away. Yet the challenges are as immense as the possibilities. Most solutions suggest that these wormholes would be incredibly unstable, pinching shut in an instant. To hold one open, you would need a form of matter with negative energy density, a substance with such repulsive gravity that it could prop the throat of the wormhole apart. Physicists like Kip Thorne have explored whether this exotic matter, a quantum field phenomenon, could theoretically exist in sufficient quantities. Even if it could, the moment you tried to use a wormhole for time travel, you would confront devastating paradoxes. What happens if you travel back and prevent your own journey? The consistency of cause and effect, the very foundation of reality, begins to unravel. These are not proposals for a future technology. They are thought experiments that press at the absolute limits of our physical theories. They force us to ask what the universe truly allows. Is time travel a logical impossibility that the laws of physics inherently forbid? Or is it merely an engineering problem on a cosmic scale? The value of these speculations lies not in building a time machine, but in what they reveal about the nature of spacetime itself. By exploring these ultimate extremes, we are testing the resilience of general relativity and searching for the point where it finally breaks, giving way to a deeper, more complete theory of quantum gravity. The shadow of the cosmos holds a deeper darkness, one that black holes might help us finally understand. For decades, astronomers have known that galaxies are held together by an invisible gravitational glue, a substance we call dark matter. Its presence is felt everywhere, dictating the rotation of stars and the bending of light, yet its true nature remains one of the greatest mysteries in science. Could the answer lie not in an exotic new particle, but in the ancient black holes we have already contemplated? Primordial black holes, those hypothetical relics from the universe's first moments, are compelling candidates for this missing cosmic mass. While we know that the stellar mass black holes formed from dying stars are far too rare to account for all dark matter, a vast, unseen population of smaller primordial black holes could be drifting through galactic halos right now. Their collective gravity would perfectly explain why galaxies spin as fast as they do without flying apart. This idea elegantly merges two profound puzzles into one, suggesting that the dark matter shaping the cosmos could be made of countless dark fossils. How do we search for something so elusive? One powerful method is gravitational microlensing. If a primordial black hole, perhaps with the mass of an asteroid, were to pass directly in front of a distant star, its gravity would act as a tiny lens, focusing the starlight and causing the star to temporarily brighten. Large-scale surveys that monitor millions of stars have looked for these characteristic flashes, and so far, they have not found enough to suggest that such black holes make up all of dark matter. These observations place strict limits, telling us that if primordial black holes exist, they can only account for a fraction of the unseen mass. Another crucial constraint comes from the cosmic microwave background, the ancient afterglow of the Big Bang. If too many small black holes were evaporating in the early universe, their final bursts of Hawking radiation would have left a distinct imprint on this primordial light, a distortion we do not observe. The data from gravitational wave observatories like LIGO adds another layer to this investigation. The rate of black hole mergers we have detected implies a certain population of stellar mass objects, but it does not rule out a separate, quieter population of smaller primordial black holes that would not produce such detectable collisions. This search extends to the very formation of cosmic structure. Could dark matter halos themselves have provided the seeds for black hole formation? In the dense cores of these invisible halos, gravitational collapse might have occurred, creating black holes directly from the dark stuff of the universe. The potential interaction is a two-way street, a gravitational conversation where black holes influence the distribution of dark matter, and dark matter guides the growth and motion of black holes. Exploring this deep connection forces cosmology and black hole physics to speak the same language. It urges us to look for indirect signatures, for the subtle ways a hidden population of black holes would sculpt the large-scale structure of the universe, or leave faint trails in the data from future, more sensitive telescopes. The profound implication is that the darkness we have been searching for might not be a cloud of unknown particles, but a universe teeming with ancient, dark points of gravity, a cosmic answer written in the void. Deep within the black hole's heart, a hidden connection weaves the fabric of reality together. This is the domain of quantum entanglement, where two particles can become so deeply linked that the state of one instantly influences the other, no matter the distance separating them. It is a phenomenon Einstein famously called spooky action at a distance, and it may be the key to understanding the black hole's interior. Recent theoretical work suggests that the particles inside a black hole are not isolated. They are profoundly entangled with the Hawking radiation being emitted outside. This delicate quantum thread could be the mechanism that preserves information, resolving the long-standing paradox by subtly encoding the history of what fell in onto the outgoing radiation. The information is not lost, it is transferred, woven into the fabric of the universe through a cosmic tapestry of entanglement. This idea reaches its most radical form in a proposal known as ER equals EPR. It suggests that two entangled particles are not just mysteriously connected, they are literally linked by a microscopic wormhole, a bridge in spacetime geometry. In this breathtaking vision, quantum entanglement and the fabric of spacetime are two sides of the same coin. The spooky connection of quantum mechanics is physically realized as a tiny, non-traversable tunnel through the universe. For a black hole, this implies that its interior might be geometrically connected to the radiation it emits, a profound blending of quantum theory and general relativity that redefines our picture of reality. The mathematics of this connection is equally compelling. The degree of entanglement between the inside and outside of a black hole, a quantity called entanglement entropy, is directly proportional to the area of its event horizon. This is not a coincidence. It reinforces the idea that the horizon is not a mere boundary. but an active information processing surface. The vast entropy of a black hole, the unimaginable amount of information it contains, is a measure of its quantum entanglement with the rest of the universe. This points toward a revolutionary concept that spacetime itself may not be fundamental. Instead, the three-dimensional world we experience could emerge from a more basic, two-dimensional quantum reality, much like a three-dimensional hologram projects from a flat surface. Testing these extraordinary ideas requires tools from the future, and they are already being developed. Scientists are now using quantum computers to simulate tiny, simplified black holes. By carefully entangling qubits, the basic units of quantum information, they can create laboratory models of event horizons and watch how information behaves. These are not real black holes, of course, but they are analog systems that obey the same quantum rules. Early experiments have shown that information can indeed scramble and reappear in the simulated Hawking radiation, just as the theories predict. It is a tentative but thrilling step toward validating that entanglement really can save information from a cosmic demise. This quantum perspective transforms black holes from simple gravitational pits into the ultimate laboratories for fundamental law. They are no longer just tests of gravity, but probes of how information, geometry, and quantum mechanics unite to build the stage of reality itself. The insights gained from their dark interiors are guiding us toward a unified theory of nature, suggesting that the key to understanding the cosmos lies not in looking out at the stars, but in deciphering the invisible threads that connect everything. What other fundamental truths are waiting to be uncovered in the quantum weave of a black hole's heart? That dark shadow at the heart of the M87 image is more than a silhouette. It is a precise cosmic measurement. This shadow is cast by the event horizon against the brilliant backdrop of the accretion disk, but its exact size and shape are sculpted by a ghostly boundary just outside, a region called the Photon sphere. Here, gravity is so intense that light itself is forced into circular orbits. Photons skim this invisible sphere, some falling forever into the black hole, while others manage to escape and travel across the universe to our telescopes. It is this final, desperate orbit of light that defines the sharp edge of the shadow we see. The diameter of this shadow is not random. It is directly tied to the black hole's mass. For a simple, non-spinning black hole, the shadow is about 5.2 times wider than the event horizon itself. This relationship provides a ruler for the cosmos, allowing scientists to weigh these distant giants directly from their images. The incredible agreement between the observed shadow size in M87 and the predictions of general relativity was a monumental confirmation of Einstein's theory operating in its most extreme regime. But the story grows richer with spin. A rotating black hole described by the Kerr solution drags spacetime around it. This frame dragging distorts the photon sphere, squeezing the shadow on one side and stretching it on the other. The resulting shadow is not a perfect circle, but a lopsided silhouette. By carefully measuring this distortion, astronomers can deduce the black hole's spin, unlocking another of its fundamental properties. The simulations run by the Event Horizon Telescope team were crucial, creating millions of possible images based on different masses, spins, and orientations. The fact that the real image so closely matched these simulations tells us that our understanding of light bending in these intense gravitational fields is remarkably accurate. Future observations, especially of our own galactic center, Sagittarius a star, will refine these tests dramatically. Because Sagittarius a star is much closer, its shadow appears to change over minutes rather than days, allowing us to create a movie of its behavior. Watching how the shadow flickers and morphs as hot spots of gas whip around the photon sphere will provide a dynamic view of gravity in action. Each new black hole shadow we capture adds another data point, another test of whether general relativity holds true under every condition. This is not just about validating what we know, it is about searching for the tiny deviations that might point toward new physics. The silent, dark circle in an image is a direct window into the heart of gravity, a celestial laboratory where light itself is forced to reveal the secrets of the void. The death of a star is a violent rebirth when a massive star, many times heavier than our Sun, exhausts its nuclear fuel. The delicate balance of its life ends in a catastrophic collapse. The star's core, no longer supported by the outward pressure of fusion, crushes inward under its own immense gravity. In a fraction of a second, it compresses from a sphere the size of the Earth to a ball of pure neutrons just a few miles across, a density so extreme that a single teaspoon would weigh billions of tons. This collapse releases a staggering shockwave that blasts the star's outer layers into space in a supernova explosion, briefly outshining an entire galaxy. But what remains behind determines the cosmic legacy. If the collapsing core is heavier than about 2 or 3 times the mass of our Sun, even the pressure of neutrons cannot halt the inward plunge. The core continues to collapse, vanishing from our universe and leaving behind only its gravity, a newly formed black hole. This is the primary birth channel for stellar mass black holes, a direct link between the life cycle of the largest stars and the creation of the darkest objects. What determines the final outcome? The initial mass of the star is the most critical factor, but its chemical composition, its metallicity, also plays a profound role. Stars with lower metallicity, meaning they contain fewer elements heavier than hydrogen and helium, lose less of their mass through stellar winds during their lives. This allows them to retain a heavier core right up to the moment of collapse, making them more likely to leave behind a black hole rather than a neutron star. This helps explain why we find black holes like the one in the famous Cygnus X1 system, which tips the scales at over 20 solar masses. The supernova that created it must have come from a massive, low metallicity star that managed to form a core heavy enough to cross the threshold into perpetual darkness. The mechanism of the explosion itself is a delicate dance. For a black hole to form, the supernova shockwave must be just weak enough to fail to completely blow the star apart, allowing more material to fall back onto the core, pushing it over the critical limit. This fallback is a key part of the story. In some cases, a supernova might appear unusually faint or rapid, a sign that a black hole formed directly from the collapse, swallowing much of the exploding material and dimming the celestial fireworks. We see evidence for these birth cries not only in the light of distant supernova, but also in the gravitational waves now detected from black hole mergers. Each collision we record tells us about the masses of the original black holes, providing a census of what the stellar graveyard looks like. The prevalence of black holes in the 20 to 40 solar mass range challenges older models and suggests that the supernova process in the early universe was capable of producing remarkably heavy cores. Every stellar death is a cosmic lottery, with the prize being either a dense neutron star or a gateway to infinity. By studying these spectacular ends, we trace the origin of the dark inhabitants of our galaxy, understanding how the brilliant fire of a star's life culminates in the silent birth of a black hole. A star's final moments can be a slow and public unraveling. When one wanders too close to a supermassive black hole, it does not simply vanish. Instead, it is slowly pulled apart by an immense difference in gravity, a process known as a tidal disruption event. The force on the star's near side is vastly stronger than the force on its far side, stretching it horizontally while compressing it vertically. This cosmic spaghettification tears the star into a long, thin stream of incandescent gas. Roughly half of this stellar debris is flung away into the darkness, while the other half falls back toward the black hole, feeding a sudden, brilliant flare that can outshine its entire host galaxy for months. This spectacular death rattle is a gift to astronomers, a temporary beacon that illuminates an otherwise hidden, dormant giant at the heart of a distant galaxy. Automated sky surveys like the Zwicky Transient Facility constantly scan the heavens, their electronic eyes searching for these sudden flashes of light. When one is detected, observatories around the world and in space, like NASA's Swift satellite, swiftly turn to observe it across the entire electromagnetic spectrum. Each wavelength tells a different part of the story. The initial ultraviolet and optical light comes from the debris crashing into itself as it circularizes into a searingly hot accretion disk. As this disk forms and material spirals inward, it heats to millions of degrees, producing a torrent of X-rays. The event Assassin 14, LI, discovered in a galaxy just 290 million light-years away, provided an unprecedented laboratory. For the first time, astronomers detected a clear signature of the stellar debris being devoured, observing the telltale X-ray emissions and even catching the outflowing wind launched by the immense energy release. The duration and brightness of the flare itself act as a cosmic scale. A more massive black hole will produce a longer, slower flare as the tidal forces act over a larger area and the debris takes longer to fall in. By studying the light curve of these events, scientists can weigh the invisible monster responsible, building a census of black hole masses across the universe. How much do these violent meals actually contribute to a black hole's growth over billions of years? While a single star is a small snack for a supermassive giant, the cumulative effect of countless disruptions throughout cosmic history may represent a significant portion of its final mass, especially for black holes in quiet galaxies with less ambient gas to consume. These cataclysms are more than just destructive spectacles. They are fundamental experiments in accretion physics, revealing how matter behaves under the most extreme gravitational duress and shining a fleeting light on the dark, quiet majority of black holes that would otherwise remain forever hidden in the void. Our universe might be a mere slice of a far grander cosmic reality. String theory, one of the leading candidates for a theory of everything, suggests that the fundamental fabric of our cosmos is woven from tiny, vibrating strings, and that this reality requires more than the three spatial dimensions we experience. It proposes the existence of 6 or 7 compact, hidden dimensions, curled up at scales far too small for us to perceive directly. Within this radical framework, black holes are completely reimagined. They would not be simple 4-dimensional spheres, but complex higher-dimensional objects, and their properties could be dramatically different from those predicted by Einstein alone. In a universe with large extra dimensions, the force of gravity could spread into these hidden realms, fundamentally altering how black holes form and behave. The energy required to create a tiny, micro-black hole could be much lower than we once thought, potentially within the reach of our most powerful particle accelerators like the Large Hadron Collider. For a fleeting moment, scientists could create and study a black hole in a laboratory, watching as it instantly evaporates in a shower of particles, a signature that would confirm we are living in a higher dimensional cosmos. These exotic objects also provide a powerful mathematical bridge to quantum gravity through a concept known as the AD/S/CFT correspondence. This is a profound duality, a kind of cosmic dictionary, that links a gravitational theory in a warped, higher-dimensional space called anti-de Sitter space to a quantum field theory without gravity living on its lower-dimensional boundary. In this framework, a black hole in the bulk of this higher dimensional space is equivalent to a hot, dense state of quantum matter on the boundary. This means that the mysterious quantum properties of a black hole, including its immense entropy, can be understood by studying a well-defined quantum system. It is as if the entire interior of a black hole, with all its gravitational weirdness, is perfectly mirrored as a hologram on its surface. How would we detect these higher dimensional black holes in the wild? Their unique geometry would imprint a specific signature on the gravitational waves they produce when they merge. Instead of the familiar chirp of a four-dimensional collision, observatories like LIGO might one day detect a warble or a harmonic overtone that defies conventional explanation, a direct whisper from an unseen dimension. The entropy of these black holes, the amount of information they can store, would also be calculated differently, tied to the geometry of the higher dimensional space they inhabit. This speculative frontier pushes the very definition of a black hole, transforming it from a simple pit in spacetime to a key for unlocking the architecture of the cosmos. What would it mean if we confirmed their existence? It would not just rewrite physics, it would redefine our place in the universe, revealing that our familiar four-dimensional world is but a shadow on the wall of a much richer, multidimensional reality. The silent finality of an event horizon might be an illusion. Scientists are now listening for faint repetitions in the wake of a black hole merger, subtle gravitational wave echoes that would shatter our standard picture. These echoes could be the signature of something stranger than a black hole, an exotic compact object without a true singularity at its core. Imagine a gravistar, a hypothetical object where the collapse is halted by a core of dark energy, or a fuzzball, a string theory construct where the entire interior is a tangled web of vibrating strings with no smooth spacetime inside. These entities would not have a sharp event horizon, but rather a slightly reflective quantum surface. When the gravitational waves from a merger hit this surface, a tiny fraction would bounce back, creating a delayed echo of the original cosmic crash. Researchers meticulously scour the data from LIGO and Virgo for these telltale repeating signals. While a few tantalizing candidates have emerged, the results remain inconclusive, buried in statistical noise. The hunt itself, however, is revolutionary. A confirmed echo would be a direct observation of quantum gravity effects, a modification to Einstein's general relativity in its most extreme domain. It would mean that event horizons are not perfect one-way streets, but are somehow porous, allowing information about what fell in to slowly leak back out over millennia. This would elegantly resolve the information paradox, suggesting that nothing is ever truly lost behind a dark curtain. How would this change our understanding of a black hole's interior? The terrifying singularity would be replaced by a dense, exotic state of matter, a quantum structure that obeys the laws of physics rather than breaking them. The search for these echoes is pushing observational physics into uncharted territory, where every faint whisper in the data could be a hint of phenomena beyond our standard models, a glimpse into the quantum nature of spacetime itself. The universe has drawn a line in the sand for black holes, a forbidden zone where none should exist, between roughly 50 and 120 times the mass of our Sun. A cataclysm called a pair instability supernova was thought to vaporize dying stars completely, leaving nothing behind to collapse. This created a clear mass gap in our cosmic census, an empty stretch on the scale of stellar remnants. Then, the gravitational wave observatories listened, and the silence was broken. The event known as GW190521 told a story of an 85 solar mass black hole, an object that by all rights should not be there, merging with another to create an even larger anomaly. Its very existence is a direct challenge to our understanding of how the most massive stars die. How did this forbidden giant form? One compelling path is through a cosmic chain reaction, a hierarchical merger within a dense star cluster. Imagine one black hole merging with another to form a new, heavier object. That new black hole then lurks in the cluster, waiting for another partner, and merges again, steadily climbing the mass scale and stepping right over the theoretical gap. It is a way to build a heavy black hole not from a single star, but from the assembled pieces of its predecessors. Another possibility is that the physics of supernova is more complex than we knew. Perhaps the metallicity of the parent star or the precise mechanics of its final explosion allowed it to bypass the pair instability process entirely, collapsing directly into a black hole that defies the old categories. Astrophysicists are now revising their stellar models, inputting this new, unexpected data to see which variables can create such an outlier. The implications ripple outward, forcing us to reconsider the limits of stellar evolution itself. What other assumptions about the life and death of stars are waiting to be overturned? Each surprising mass recorded by LIGO and Virgo is not just a data point. It is a message that the cosmos is more inventive, more violent, and more mysterious than our textbooks ever allowed. These jets of plasma and radiation are not just spectacular light shows. They are the most powerful particle accelerators in the universe. They can hurl subatomic fragments across cosmic distances with energies far beyond what our most advanced machines, like the Large Hadron Collider, can ever hope to achieve. These are ultra-high-energy cosmic rays, mysterious atomic nuclei that streak through the void at nearly the speed of light, each one carrying the immense power of a professionally thrown baseball packed into a single, minuscule particle. For decades, their origin was one of astrophysics' greatest puzzles. How could nature accelerate particles to such phenomenal energies? The answer appears to lie within the violent hearts of active galaxies, where supermassive black holes launch their relativistic jets. Observations from facilities like the Pierre Auger Observatory, a vast cosmic ray detector array in Argentina, have now traced the paths of the very highest energy cosmic rays back to broad regions of space outside our own galaxy. Their trajectories point toward sources like the famous active galaxy Centaurus A, which possesses a massive, clearly visible jet erupting from its central black hole. The acceleration mechanism is thought to be a natural and relentless process called diffusive shock acceleration. Picture a charged particle, a proton for instance, caught in the turbulent magnetic fields within a jet. It bounces back and forth across a shockwave, the jet's internal sonic boom, each crossing giving it another kick of energy, much like a ball being volleyed ever faster between two approaching rackets. Over time, the particle is confined by these magnetic walls, gaining staggering energy until it finally escapes the jet's grip to begin its multi-million-year journey across intergalactic space. This profound connection reveals that black holes are not just consumers of matter, but also prolific producers of the most energetic particles in the cosmos. They are fundamental drivers of the high-energy universe, their distant jets acting as natural laboratories that conduct particle physics experiments on a scale we can only hope to observe from afar. How might these cosmic rays, born from the fury of a black hole's jet, be shaping the very conditions between galaxies as they travel? A cosmic census is quietly underway, one that counts the invisible. By compiling the masses and spins of thousands of black holes, astronomers are building a demographic map of the dark population, transforming individual detections into a story of cosmic evolution. This is not just a list, it is a history book written in gravity and light. Each gravitational wave chirp from LIGO and Virgo adds a new data point, a record of a merger that happened billions of years ago. When combined with electromagnetic observations of X-ray binaries and active galactic nuclei, these points begin to form clear patterns, trends that reveal the life cycle of stars across the universe. We see that the most massive stellar black holes tend to form in environments with low metallicity, where ancient stars held onto more of their mass, leaving behind heavier corpses. The merger rate itself is a clock, telling us that the universe was a more violent and crowded place in its youth, a period of frequent cosmic collisions. Projects like the Black Hole Catalog or Black City synthesize this flood of information, estimating that our Milky Way alone may be home to millions of stellar mass black holes, most drifting silently through the dark. What does this large-scale picture reveal? It shows that black holes are not random anomalies, but integral threads in the cosmic web. Their distribution and properties are shaped by the same large-scale processes that build galaxies and clusters. The demographics of these dark objects act as a fossil record, preserving the conditions of star formation and the chemical evolution of the cosmos across billions of years. This big-picture approach contextualizes every strange outlier and every common merger, helping us understand our place in a universe whose structure is fundamentally shaped by the gravity of the unseen. Yet we do not need to travel across the cosmos to probe the edge of infinity. The strange physics of an event horizon can be recreated right here on Earth, in tabletop experiments that trap light and sound in artificial gravity wells. These are black hole analogs, ingenious laboratory systems designed to mimic the essential properties of a black hole without its crushing gravitational density. Scientists use supercooled clouds of atoms known as Bose-Einstein condensates, or even flowing water, to create a point of no return for waves. In a sonic black hole, for instance, a fluid is set into motion, flowing faster than the speed of sound. Just as nothing can escape a real black hole once it crosses the event horizon, a sound wave traveling in this fluid cannot move upstream against the current. It is dragged inward, trapped by a sonic horizon. This setup allows researchers to test one of Hawking's most startling predictions in a controlled environment. In 2019, a team led by Jeff Steinhauer reported detecting the analog of Hawking radiation in such a system. They observed that pairs of sound waves, much like the virtual particle pairs in empty space, were appearing at the sonic horizon. One partner was swallowed by the flow, while the other escaped as a thermal whisper of sound, a direct parallel to the theoretical glow of a real black hole. The measured spectrum of this radiation matched Hawking's prediction with remarkable fidelity. These analog systems are not perfect replicas, of course. They simulate the kinematics of an event horizon, the way things move at a boundary, but they do not reproduce the full, deep gravity of Einstein's theory. Their immense value lies in their controllability. A physicist can adjust the flow rate, change the fluid's properties, and run the experiment again and again, something impossible to do with a cosmic black hole millions of light years away. This allows for direct tests of how quantum fields behave near a horizon, probing the subtle interplay that gives rise to radiation and information scrambling. How can these lab studies possibly complement the grand observations from LIGO or the Event Horizon Telescope? They provide a crucial ground truth. While telescopes observe the large-scale consequences of gravity, these analog experiments isolate and test the underlying quantum mechanical processes thought to be at work. They offer a different path to the same fundamental truth, bringing the most extreme physics in the universe into the realm of experimental science. This innovative approach transforms black holes from distant mysteries into accessible phenomena, suggesting that the keys to understanding the cosmos may be found not only in the void of space, but in the quiet precision of a laboratory. The silent giant at a galaxy's core is far more than a passive occupant. It is the master architect of its cosmic home. This profound connection is written in the stars themselves, a direct correlation between the mass of a supermassive black hole and the properties of the galaxy's central bulge of stars. This tight relationship is no coincidence. It is the result of billions of years of co-evolution, a gravitational symbiosis where the black hole and its galaxy grow up together. But how does a dark object that consumes light also give birth to the brilliant structures we see? The answer lies in a powerful process known as feedback, a cosmic conversation between the black hole's immense appetite and the galaxy's capacity for creation. When a black hole actively feeds, the energy released from the infalling material is staggering. This energy does not simply vanish into the void. it is poured back into the surrounding galaxy in two primary ways, through colossal jets of particles and through immense hot winds. These outflows act as a universal regulator, heating the vast reservoirs of cold gas that are the raw material for new stars. By making this gas too hot and turbulent to collapse, the black hole effectively puts the brakes on star formation, a process astronomers call quenching. Imagine a galaxy without this regulatory hand. It would form stars in an uncontrolled frenzy, rapidly exhausting its gas supply and burning out in a short, brilliant flash. The result would be a universe filled with very different, much larger and disorganized galaxies, lacking the elegant structures like the grand spirals we observe. This feedback cycle is not constant, it pulses with activity. A period of intense feeding and feedback is often followed by a long, quiet quiescence, allowing the galaxy to slowly cool and eventually form a new generation of stars in a more measured way. This cycle of activity and rest, driven by the central black hole, helps sculpt the diverse population of galaxies we see today, from fiery, star-forming spirals to quiet, red and dead ellipticals. What triggers these violent feedback cycles? It could be a galactic merger which funnels vast amounts of gas toward the center, awakening the sleeping giant and igniting a quasar. The energy output from that quasar then blows away the remaining gas, halting both its own growth and the formation of new stars, leaving behind a more settled galaxy. This role transforms our view of black holes from simple destroyers to essential creators. They are the gravitational hearts of galaxies, their rhythmic pulses of energy influencing the birth of stars, the distribution of matter, and the ultimate fate of their cosmic homes. This deep connection ties together the physics of gravity, the flow of energy, and the grand narrative of cosmic evolution, revealing that the largest structures in the universe are fundamentally shaped by the smallest points of infinite density. The idea of a dark star first shimmered into existence not with Einstein, but in the mind of an English clergyman named John Michell in 1783. He reasoned that if a star were sufficiently massive and compact, its gravitational pull would be so immense that not even light could escape. He called these objects dark stars, a brilliant leap of intuition that lay dormant for over a century, waiting for a theory of gravity powerful enough to give it form. That theory arrived with Albert Einstein's general relativity in 1915. Mere months later, the German physicist Karl Schwarzschild, while serving on the Russian front during the war, found a solution to Einstein's complex equations. His work described a point of infinite density, a singularity, surrounded by a boundary from which no light could return, the event horizon. At first, this was seen as a mathematical curiosity, a physical impossibility. Even Einstein himself was skeptical that such bizarre objects could actually form in nature. The theoretical foundation solidified in the 1930s when J. Robert Oppenheimer and his student Hartland Snyder calculated the final stage of a massive star's collapse. They showed that under its own weight, a star's core could indeed crush itself out of our visible universe, leaving behind only its gravitational shadow. Still, the concept remained on the fringes of physics, a theoretical ghost. It needed a name to give it substance, and that came from the charismatic physicist John Wheeler, who popularized the term black hole in 1967. The name stuck, transforming an abstract mathematical concept into a tangible cosmic entity. At the same time, Roger Penrose developed his groundbreaking singularity theorems, proving that under general relativity, the formation of a singularity was not just possible, but inevitable under certain conditions. The final piece of the puzzle fell into place with observational evidence. In 1971, astronomers pinpointed the powerful X-ray source Cygnus X1. The data revealed a massive, unseen object pulling material from a companion star, heating it to millions of degrees and producing the brilliant X-ray glow. The invisible partner was far too heavy to be anything but a black hole. This was the first compelling identification of a black hole in our galaxy, a discovery that moved these objects from the realm of mathematical speculation to the forefront of observational astronomy. How did this long journey of theoretical advances shape our modern understanding? It demonstrates that science often progresses through a slow accumulation of insight, where a forgotten idea can blossom centuries later into a cornerstone of our cosmic reality. The initial skepticism of brilliant minds gives way to a new consensus, built equation by equation and observation by observation, until the impossible becomes an established fact of the universe. We have journeyed from the first tremor of a gravitational wave to the faint glow of Hawking radiation, from the fiery ring of a shadow to the quantum threads of entanglement. These 25 discoveries are far more than a collection of facts. They are a fundamental rewriting of our cosmic story. Black holes are no longer just the monsters of the void. They are the engines of galaxies, the laboratories for quantum gravity, and the keepers of the universe's deepest secrets. Each revelation, from the forbidden giants in the mass gap to the potential for hidden dimensions, forces our laws of physics to evolve, bending and stretching to accommodate a reality far stranger than we ever dreamed. This relentless pursuit of understanding, driven by both mathematics and observation, reminds us that the universe is not a puzzle to be solved, but a mystery to be embraced. The awe we feel is not just for the immense power of these objects, but for the human curiosity that dares to decipher them. As our tools grow sharper and our theories more profound, the next great breakthrough in science will almost certainly emerge from the darkness. The journey is far from over. If these cosmic mysteries captivate you as they do us, consider subscribing for more explorations into the wonders of space. We would love to hear which discovery reshaped your view of the cosmos, so please share your thoughts in the comments below.